Hi there. Thanks for coming. My name is Matt Adams with a place called The Fourth Pig. We do green environmental construction, and we're going to do this a little more formally, mostly because we can record the audio and the slides and put it up on the internet for the people that called us and said they couldn't make it, so thank you for coming. We also want to thank Burlington Green for putting out the word for us. I want to see who's here, and just show of hands, you can raise it more than once. Homeowners? Yeah, ooh, there we go. Architects? Ooh, couple. Developers? Any officials that want to admit to it? No? Elected officials, municipalities, building officials, inspectors, there you go. Thank you. Any other categories I'm missing? Parents? No. Environmentalists? Woo! Non-environmentalists? Today I'll do, real introductions when we get to each person, but maybe sort of raise your hand. We have Greg LeBay here from the Green Group, and Tara Wong from Stone's Throw Design, and Ed Harris from Passive House, Ontario. Where are you, Ed? Over there. And Marion, I just called you Harris. Sorry, sir. And then Ann is here, over there. This is Ann Stewart's the lead investigator and founder of Environmental Health Consulting. I'll give a little blurb for our non-speakers. They conduct on-site assessment of businesses, homes, cottages, and boats to help remove or reduce the items with the most risk to human health. And Ann has an environmental health degree, certified public health inspector, and building biologist, and a professional member of the Canadian Institute for Public Health Inspectors. So she's around, and you can talk to her afterwards about all this kind of work. And hiding in the corner back there is Kevin Royce, who owns and operates Eco Building Resource. He's a source for a lot of people that do construction and renovation using environmental, sound and healthy building products. He's been around for like 25 years in the industry, and he knows a lot about them. So he's hiding back there, but Kevin, talk to him afterwards. So today is a lot about the sort of how, and I'm going to give a moment or two about the why. And first, though, I'm going to give a little bit about who the Fourth Pig is, because this is my only chance to do that. We're a small, environmentally focused construction company. We do renovations and construction work. We like to say natural, beautiful, affordable, sustainable. This is a little shot of a house we did in Muskoka where we renovated it, in part wrapping it with straw bales to give it better insulation factor, and that's the outside there with some beautiful windows. We're actually a nonprofit. We have a mission statement, and this is our mission statement: to foster ecologically balanced methods of construction and energy production in order to promote more sustainable and healthy communities. That's another shot from the inside of that Muskoka house. I'm going to be very quick here. This is from, and I think Terrell's going to talk a little bit more about this house later, but this is from a house in downtown Toronto that's actually got a fair amount of straw bale walls in it. And we work with straw bale, but we also do non-straw bale work and focus on environmental products that are friendly and products that promote a sort of healthier living environment. So that's my ad. Past the ad now, very quickly on the why. When we started the Fourth Pig in 2007, we figured there'd be thousands and thousands of green builders by this time, and there's not, but it's becoming more prevalent. And our argument was, why build green? And the huge one for us is the environment. This is a quote from the New Scientist magazine. They're saying, people don't talk about construction when they talk about climate change. They talk about greenhouse gases. We talk about, automobiles and power plants, but a huge percentage of those come from the construction industry. This is a quote from the United Nations. The building sector contributes 30% of annual greenhouse gases and consumes up to 40% of all energy. These are enormous numbers, absolutely enormous numbers.
Is that taking account of production?
I believe it does. So again, another quote from the UN: countries will not meet emission reduction targets without supporting energy efficient gains in the building sector. And then quickly, I have a couple Canadian numbers. These numbers are actually even worse. These are Industry Canada's numbers. I checked them the other day. So these are the most recent numbers on the Industry Canada website. 50% of extracted natural resources, 1/3 of the country's energy use, 25% of landfill waste, 10% airborne particulate, and 45% of greenhouse gases. So that's one of the major motivators, at least from our perspective, is how can we make, build, and renovate buildings in a way that better promotes a sustainable future. And then very quickly, here are the things that can happen in a green building. Your energy efficiency can go up, your water efficiency goes up, your air quality can go up, your health and well-being can go up, and of course the value of the building can go up, which is important to a lot of folks who are trying to resell or developers. And then what goes down? Your energy costs, your operating costs, your building depreciation rate. In fact, there was just a study the other day, came out of Harvard University, saying that it was looking at green buildings, and they had various definitions of that, and low-income people that lived in them, and the rate of, they were studying asthma, the rate of asthma attacks went down significantly in what was deemed green buildings. That's it for me. I promised I'd be very, very short, but that's kind of our overall why for some of us. We'll have 3 different speakers come up, Greg and Ed and Terrell, and then I'll ask you to hold most of your questions to the end, and so we can get through folks, and then we can answer all your questions, and then we can mingle afterwards. You can ask some more questions. So, Greg LeBay is co-owner of Blue Green Consulting Group, specializing in the testing and design phase optimization of high-performance buildings. He works with architects and builders to optimize the energy performance of new or existing buildings through detailed energy modeling and site testing. Greg also does building envelope failure diagnostics as well as ventilation system commissioning. He recently completed a research project on vintage housing stock with Humber College and Ryerson University. Greg contributes to Home Energy Magazine, Green Building Advisor, and his blog was nominated by Green Building Advisor for Blogs We Like. He's also on the OHBA's Institute of Building Excellence Trainers, and finally he's in the Technical Steering Committee for Building Performance Institute Canada, and is also a trainer for the Sustainable Building Advisor Certification. Greg knows what he's doing. We work with him as much as we can.
Okay. I made you, that was a long bio.
Not the longest.
Okay. Thanks for coming, everyone. It's good, always nice to have people come out and listen to what you have to say. So we're pleased to be here in Burlington. So about Blue Green Group, we're building envelope specialists. We optimize buildings using energy simulations, and that is, in the planning phase as opposed to waiting till the building's already constructed. So we try to tweak the design with the architect or the designer, and we test new and existing building enclosures for performance. And we also do diagnostics where building failures occur either in windows and attics, ice damming, mold, condensation issues, that kind of thing, to try and find what's going on. And we also commission ventilation systems for houses. So we work in the design phase, the building phase, and the commissioning phases. So some insights that I want to talk with you about briefly tonight. I realize we don't have a lot of time, and I like to talk a lot, so I'm going to try and keep it down, but I've got 5 points here. How does my house lose energy? I'll go through some basics with you, and plan. As it's the same thing as location. Complexity breeds inefficiency, and test, don't guess, and clear the air. So we'll start from the top. Just the basics. We're going to do a little bit of trigonometry here, a little calculus for you guys, hopefully demystify some stuff. So the concepts of passive house. So the concepts of passive house are really nicely illustrated by these diagrams put out by Albert Reiter and Tightness Architects. So in the blue here, you can see the thick envelope of the building is reducing heat loss through super insulation. The next one is the continuous red line. And the continuous red line on any architect's diagram is the air barrier. And the air barrier can be on the inside, it can be on the outside, but it is always continuous, so you can never let your pen off the paper. That's the trick. And finally, at the end is reducing heat loss at the corners, thermal bridging. So every time there's a structural element, we put insulation on one side or the other of it. The next thing that the concept of passive house teaches is that we capture in that building envelope the heat of the occupants inside. We also capture the heat of the fridge, the stove, all that heat stays inside the house during the wintertime. And of course, we harvest sun's energy, and we harvest the sun's energy strategically by having calculated, this is what architects are fantastic at, calculating the position of an overhang so that you maximize south-facing solar heat gain during the winter and minimize it during the summer. And finally, the big key here in all super efficient houses is having an outstanding ventilation system. And these are the lungs of the house, as a lot of people call them. So the story goes like this. In the 19th century, we lived in houses with skinny walls. Well, not necessarily split skinny, but skinny in terms of our value. You wore a big sweater, you made a big fire, you had a big chimney. See, no chimney here. On the in the middle here is the technological hubris of the 20th century, where my man in the middle has no sweater on, but you need a PhD in mechanical engineering to operate this house. Whereas on the end, the 21st century belongs to small systems, super well-assembled building envelope. So how does heat move? It moves through conduction, convection, and radiation. And of course, the wind has effects. Wind can push heat in and out of a house, air out of a house if it's not airtight. Same thing with stack effect, where it's the same concept that pushes a balloon up into the sky here. So the vectoral forces here on the top half of the house are much bigger. So if you've got a tall house, you'll get a lot of stack effect. If your house is airtight, it doesn't matter. There's still stack effect, but there's no air exchange. And the last is combustion and ventilation. And the whole passive house tends to de-emphasize mechanical equipment so that we don't tip the apple cart on the ventilation systems inside the house. And a lot of people always have this notion that, when you stand on the floor of your house, well, you only lose heat up. There's this whole idea that heat only goes up. But the truth is that we lose heat in all directions, through the floor, through the walls, through air leakage, through the attic, through the windows. So heat moves in all directions. It is true that buoyant air does move up. So first of the insights is plan. And we like to use computers to do energy simulations so that we can predict what a building's energy consumption is going to be like before it's built. It's a pretty powerful system when you could do that. And simulations take the guesswork out of selecting upgrade features for a house. And if you can do that, you can say, well, this feature costs an extra $10,000. What am I going to save? Very accounting, very mathematically based approach to making upgrade decisions. So a good detailed plan is easy to follow, will save you money, and it will avoid disputes with the builder or trades in the long term. So plan. So here's an example, and I ask you, well, which one of these two houses is more efficient? We don't know. We don't know until we test, until we measure. So that's the whole idea with doing energy simulations, is that we can find out what is the difference between one building and the next. It could be a 14,000 square foot cottage, which we've done, or it could be, a 1,400 square foot house, that's perfectly square. So energy simulation is a very powerful tool. Second insight is keeping it simple. Avoid complexity in the physical shape of the building and avoiding complexity in the mechanical systems. So we try to de-emphasize complexity, making it simple for people. And it's not to say that building high performance has to be boring. You have to be creative, and we have to build buildings that we love, because if we love the buildings, we'll take care of them, they last longer. That's the truth of it. So here's a pro tip. So a simple shaped, well-built home needs small mechanical systems, and it's easier to maintain and costs less to build. So this whole concept of origami and complexity, the architect Bill Rose wrote me back after I wrote an article in Green Building Advisor. He said, how dare you compare that architecture to origami? You're insulting origami. And it's a funny thing, because if you go to the ROM after the snow, you can't get in. You can't get into the shop. Okay, this is bad design. Somebody totally didn't think of the climate for this building. This building may have worked in Acapulco where there's no snow, but here in Toronto, If it snows and there's a lot of snow, it's actually dangerous to be around because the snow comes falling off the building. Crushes people. I'm waiting for that headline to come out. Crushes 5-year-old after snow. And and of course, the flux capacitor, right? And this is not a joke. I took this from Energy Vanguard's website. I do have pictures as well, but sometimes, when you're insulting people, and it's good to not insult people that also put bread on the table. So I took Energy Vanguard's advice or picture here. But this is sometimes you need a PhD to operate these houses. Things get really complicated in houses. So the next thing is, when we get into contemporary houses, so we all know what this is. This is the room above the garage. You can see there's a lot of exposed floor here, and the ductwork. You see the ductwork in here. You see the metal ductwork. So that's all going to be foamed in. That's fine, but it's really, you could design that out of the design in the first place. Now, it is tough in the suburbs. I understand everyone wants the car, and there's a lifestyle approach. And this is probably not what most people in this room would necessarily opt for in terms of design, but just to sort of lay it out there. So the bonus room, you can design that out with good design. And this is what it looks like here, close up. This is, believe it or not, outside the front porch, and this is a bathroom here. You can see a powder-coated steel beam right here holding up the brick above the front porch, and you can see a duct. These are two ducts that come out above the front porch, and this is going to be spray foam, but I guarantee you these things are almost going to be bare metal, and they will always be uncomfortable in this bathroom. I believe that the crapper was right here, and I've got a crapper story for you coming up. So the mini side attic. So there's no shortage of mini side attics, bump outs, features so right here you can see there's like a little. This main floor bump out here, there's a little attic in here. In 1999, I was hired at Greensaver to go and fix Toronto community housing houses. And my job was to get into crawl spaces and attics. I'm a farm boy, and I was working fine in chemistry. I was making good money in a lab wearing a white coat. And then I decided to have a career change. I had an epiphany. And so here I was, white, pristine lab coat, where the glassware was, all ultra clean, to crawl spaces that had dead things in them. I learned a lot. But what I can tell you is a past insulator is that somebody has to insulate this attic. And I guarantee you that it will be done very poorly. So these details here. So if we follow this corner here, this corner comes down, the brick comes down, and then, it doesn't align. The corner jogged out. Why did it jog out? It jogged out because right here there's a small attic. We're going to call it a small attic. Okay? There's also a beam. There's a steel beam that goes across here. Okay? So that's steel. It's a very compromised detail. It's hard to detail and get a good airtight and thermal bridge free assembly. So these are the kinds of details that architects who are aware design it. They avoid all these details. The bump out. And I joke here because when my coffee's here, once the sink is installed here, I can't even reach. I'm too short. I can't even reach the coffee. If that was my coffee there, I wouldn't even be able to reach it and open the window. So these bump outs, they cost a lot in terms of efficiency. Okay. Skylights are another one. When mechanical designers design houses, they have to calculate in their calculation the square footage of wall and the R value of wall. Well, some of these columns can be, 17, 20 feet tall and 17, 20 feet long. That's wall area that's never accounted for in the building design heat loss, heat gain. There's always condensation that takes place. Skylights, there's ways to do them properly, but tall columnar is usually not one of them. The risk. This one here, I was there, a pair of French-Canadian guys were installing the drywall. This was 2 feet wide. And I always say it's one canoe by one canoe. It was like you could literally fit a canoe up and across. It was 17 by 17, and they were trying to fit the drywall up and nail it to one side in 2 foot wide triangular. It's crazy. This goes on today in construction sites all around Toronto. Columns. So the bigger your house is, the more point loads you have around the perimeter, the more thermal bridging. Again, this chimney here, one would think, well, what kind of fuel are we burning here? Any guesses? Someone else. Come on, someone say wood, because you need a chimney. Well, thank you, Matt. Thanks, but you're wrong, Matt. Oh, jeez, it's natural gas. Oh my gosh, how can we tell? Well, it's got a little vent right here, right? Is that it? Yeah, it's right in that area. I can't tell from this angle here. So this is a feature that somebody paid, a couple $1,000s. Like they interrupted the eave here, and they had to jog out the wall. That's a lot of expense for something that is just, it's like this jacket. It's just a fashion statement. Thank you. The frozen crapper caper. And I know, it's rude. So again, we've got this bump out here. So a client called me up and he said, when it's really windy and cold out, I can't flush the toilet. That is a problem. So I'm going to show you something here. Here's the toilet, the frozen toilet. And what do we have here? A little heater.
Yeah.
Is that a danger? Is that like next to the bathtub? Right next to the bathtub? Is that dangerous? Is that good building design? So somebody wanted this bump out just to change it up. We're just going to change it up. Honey, I'm going to put a different jacket on and a different tie. We're just going to change it up tonight. So this is what this is. This is all about just for the hell of it. We're going to put this little feature in. And this is what it looks like on the inside. The problem is it's making the toilet freeze. And it's all bad design because the floor joists come out like this. The contractor didn't seal it on the end. And this is what it looks like when under normal conditions, under normal conditions, we don't see any red hot spots here, but when I pressurize the house with my blower door and take a second image, we see a hot spot here and a hot spot here, So these two hot spots are me forcing the warm air outside of the building here, causing a peak here and a peak here that weren't there, So what we see here is under natural conditions, if the wind is blowing in the right direction, the air gets in here and it overwhelms the water line and freezes the water line. So all of this stuff can be designed out. And that's what we're saying, design it out by good plan. Plan. So the third point that I want to make is test, don't guess. So no testing. If you're not testing, you're guessing, really. I know, it's a cheesy sort of self-promotion. Airtightness tests are mandatory in high-performance homes. And I always tell people that the testing just doesn't hurt. It's safe. Homeowners like the added scrutiny, especially pre-drywall. We like to do pre-drywall tests because when the drywall is not on, you can fix things. Once the drywall is on, it's too late. You can't change anything. Well, you can, but you have to rip it down. And then there's the benefits of an airtight home. So what are the benefits? There's durability, comfort, energy savings, and health. And what are the risks? The risks are discomfort, wasted energy, mold, condensation, and repairs. We don't want that. So my house, which is an old house in the High Park area, or actually in the Junction area of Toronto, is like this. It leaks a lot. In the 1980s, we started making houses a little bit more airtight, but not necessarily on purpose. And then Energy Star R2000, they're starting to get more airtight. And then the Passive House. So this is all the heat loss due to air leakage. And you can see Passive House is really focused, singularly focused on making buildings super airtight. You test your shoes, why not your house? Try before you buy. Pod lights. So this is a pod light, if you haven't seen it, a pod light before it's installed, before the drywall is installed, it's from the attic side. And this is what it looks like in my neighbor's house, which is just really sad. Oh, it's a video and it's not showing. I'm sorry about that. I should have. Anyways, you can see the smoke just pouring in. I'm depressurizing the house, and there's a lot of air leakage happening. And yeah, it's too bad. All of this stuff can be avoided if you test before the drywall goes on. Spray foam. We like to say that spray foam. A lot of people think it's the silver bullet, that it's going to be the one thing that's going to solve all of their problems. But you have to test it. You have to actually physically inspect it, make sure that the spray foam got everywhere and is adhered to everything and is continuous. Sometimes it flakes off. It doesn't like to stick. Checking your foam for depth. This is in an attic in Mississauga. This is a 4,000 square foot footprint house. So it was a very large house. In the attic, there was a lot of ductwork, and I had to have the spray foam contractor come back 4 times to apply foam to missed spots. I kept on going up there, magic marker, come on back, do this section, do this section. So again, spray foam, is it really air sealed? We can look at the nice fluffy stuff here. This is a beam. There's a lot of stuff that could have been changed here in terms of the design. So plan. And again, here you can see right here that the foam is delaminating. And this is common with a half-pound foam if it's not applied properly. Half-pound foam really moves quite a bit. Finally, the last point that I want to talk about is, let's clearly air. Let's put a price on distributed fresh air. And what I say about that is it's very important as houses move to become more airtight, that we actually invest in good mechanical ventilation systems. So efficient homes need to be airtight. Exhaust-only ventilation sucks, warns Dr. Joe Steebrook. I don't know if you know Joe Steebrook, U of T graduate, engineer, bigwig building scientist down in Massachusetts. Writes a lot of interesting papers as part of Building Science Corp. Houses don't need to breathe, but the occupants do. And that's something that everyone needs to pay attention to. Ventilation is not something you let the building shell take care of through leakage or having a window open. Ventilation needs to be dosed precisely. And I always tell architects that, especially, that think of a dose. It's just like if I ask you, how many cups of water a day do you need to stay alive? And I ask you guys, I want somebody to throw me not Ed, because you know the answer. How many cups of water? 8 cups. Okay, so how many cubic feet per minute per occupant of fresh air do you need in order for the air in your house not to be stinky? They've engineered this through smell tests. Hockey bags. Just give me a number. Cubic feet per minute, that's like imagine a squared off basketball. 10, did you say 10? Oh my gosh, you must be a building scientist. Yeah, I think you're right, it's 10. So we're going to do a quick experiment. We're going to take half the room. If you guys could just, for a couple of minutes, stop drinking water, okay? On this side, it's going to be messy. You guys just stop breathing air, okay? We're just going to do this for 3 minutes, starting now. How are you guys doing? Okay, so we realize that we can live a long time without fresh water, but we can't live long without air, without oxygen specifically, and it's a bonus to have fresh air. I just learned yesterday, I was watching a National Geographic a video on YouTube about submarines, and specifically about a US-made submarine, the biggest submarine in the world, nuclear submarine, and they were talking about making air underwater. Because I always wondered, how long would it take me to deplete the oxygen in a certain amount of air in a day? And they told me, the National Geographic show gave me the answer. It was 12 cubic meters of air for one human to deplete all of the oxygen within that air. Now that's not fresh air. That's 12 cubic meters of air for one person just to survive basic functioning on the ground, just breathing. So that's not enjoying your life, and that's not working out on a treadmill in the basement. So the results of our experiment showed that, we can't, it's more crucial to have fresh air than it is to have good water. Yet, as North Americans, we've all seen it. You go to the grocery store and there's people pushing shopping carts full of water. When we have, water in bottles, when we have a tap that gives us municipally safe, brilliant drinking water, except in certain communities, which is a sad state of affairs. But yeah, so put a price on fresh air. So if you prefer the premium, think about ventilation. Invest in a dedicated ventilation system that has heat recovery. So those are all my points. When you go about doing a renovation or building a new house, ask yourself, where do you stand on comfort, health, and energy efficiency? Are you the kind of person that likes excellence? Do you like good, average, or are you okay with poor? So those are my points. I hope you guys didn't fall asleep. Thanks very much.